Thank you very much. I'm very pleased to be here. I think it's my third visit to Kyoto. I know it's greater than or equal to 3. And the weather here is a little different. The other 2 times were in the summer. And I think this is better. So I think the title that's in the official list of titles is slightly different, but it's the same talk. There's a recent review paper that was posted last month, which I listed over here. That's a kind of, in a sense, an extended version of this talk. So that would be a good reference. That's joint with a former postdoc, Wei Wu, who is now at Warwick University. Yes, and so I wrote to appear with quotation marks because it was semi-accepted, but we need to make some changes before it's officially accepted. Right. So this just like this this review article, this will largely be a historical review about a certain approach to the Riemann hypothesis, which is mainly due to Polya from the 1920s, but has close connections with statistical physics. Okay, and I think that at least the 2/3 of it should be understandable without practically any background. And if you have questions about analytic number theory, I almost certainly will not be able to answer them because I know very little. So the topic concerns Fourier, or I've set it up to be Laplace transforms of functions f. So forget about this term in the middle for a moment, or if you prefer, set lambda to be equal to 0 temporarily. Then this would be the two-sided Laplace transform of the function f. The functions that we'll deal with will always be non-negative and integrable over the whole real line. So for a function like that, if you multiply by the right constant to normalize it so that the total integral is not just finite but equal to 1, then you could regard that function as a probability density function. That's not particularly relevant for most of the talk, but since those of us in probability theory makes us feel more comfortable. Okay, then this Gaussian factor inside here you can think of as starting with when lambda 0, that's simply the Laplace transform of the function f, and then for small lambda this is a kind of perturbation of that Laplace transform, at least if lambda is negative, then because f was integrable already on the entire real line, then you put a negative lambda, then you have the function e to the lambda u squared f of u, which is decreasing fairly rapidly, so that the Laplace transform will not only exist for real w, will exist for complex w and be an entire function of w. So that will be true certainly for lambda negative. For some functions f, it's true even when lambda is 0, or even when lambda is positive. It depends how f of u goes to 0 at plus or minus infinity. And we will mostly be dealing with cases where the function f goes to 0 quite rapidly, so you can also make the lambda positive. In any case, for some lambdas, at least for negative lambdas, this function will be defined and an analytic function of complex w. Because the f, we'll be interested in f's which are non-negative, then sometimes we'll replace f of u du by a measure, positive measure rho of u, and And if it's normalized by the right multiplicative constant, then it would be a probability measure, but that's not that's only relevant occasionally. It also, in the cases we'll be interested in, the function f, or the measure rho, will actually be an even function with respect to replacing u by minus u. Okay, so that's the general setup, and now I'll explain to you how that setup is related to the Riemann hypothesis. Okay, so the Riemann hypothesis comes up if you take that function little f to be a very specific function, which we'll call capital phi. In fact, here's the specific function written as a explicit a convergent power series. U is just a real variable, and because this term here decreases for any real u, this decreases very rapidly with n. And then even when you multiply by these increasing coefficients, it's certainly summable, and so you have a well-defined function capital phi of u. The reason why, and this goes all the way back to Riemann's original paper in 1859, this way of organizing things. The reason this function is related to the Riemann hypothesis is that when you take that function capital phi, and now this 0 there means that e to the lambda u squared isn't there. The little lambda was 0, so it's just the Laplace transform of this function on the real line, is related to the Riemann zeta function, which is over here, by multiplying it by some other functions, a gamma function and e pi to the minus s over 2 and some little quadratic polynomial here. This modification of the Riemann zeta function is called the Riemann xi function, which Riemann studied. These extra factors there are useful for various purposes. The zeta function, besides the question of where the zeros are in the critical line, has so-called trivial zeros. The multiplication by the gamma, which has certain poles, gets rid of those trivial zeros, and also it has a kind of symmetrizing property, so that you end up with a function, this function of s is symmetric about the line 1/2. So if you change variables, making w real part of w equals 0 corresponding to the real part of s equals 1/2, which is the critical line of the zeta function. Now the imaginary axis is the critical line in the w variable, and this function of w is an even function. So that means that another way, equivalent way of saying that is that this function phi has a couple of properties which are not completely obvious. It's obvious that this is a nice convergent function of u for all real u. It's not. I said we were interested in functions little f, which were non-negative and even. Neither one is obvious for this function phi. The fact that this function phi is an even function of u, which it does not look like it is, that's the statement of Riemann's functional equation for the zeta function. If you make that statement in terms of the original zeta function instead of this xi function, it's exactly the statement that equivalent to the statement that this function phi is an even function of u. I'm going to show you in one moment a graph of this function, a numerical graph, and the graph numerically you'll see that it's a nice even function. Once you believe that it's an even function, here's a two-line proof that it's a positive function. Okay, when u is positive, it's easy to check that this prefactor here, the first term is greater than or equal to the second term when u is greater than or equal to 0. Because n to the fourth is bigger than 3/2 n squared, and well, maybe not for n equals 1, but anyway, n to the fourth pi squared is greater than or equal to 3/2 n squared pi for each n, and e to the 9u is bigger than e to the 5u for u greater than or equal to 0. So these terms that we're summing are term by term non-negative when u is positive. That's not true when u is negative, but once you accept that phi is an even function, you don't have to check it. So the claim is that this is both even and positive. And let me now verify that numerically by showing you what the graph looks like. So there's the graph of the function phi. It's not a very exciting graph. This is 0. This height here is 0. And so that of course that means the function is practically equal to 0 once u is greater than or equal to, the absolute value is greater than or equal to about 0.3. That's because that e to the minus, there's an e to the minus exponential which goes to 0 very, very rapidly. So it goes to 0 much, much faster than, say, a Gaussian density. So practically equal to 0, and you can certainly look symmetric about u equals 0. So it looks, looks something like a normal distribution, but somehow with a much faster decreasing tail behavior. Okay. Okay. So this was already in Riemann's 1859 paper without the lambda. That is so this L phi 0 is the Laplace transform of the function phi, this function, with no extra term, without that Gaussian term, and the Riemann hypothesis, because that Laplace transform is this Riemann Xi function, which is directly related to the Riemann zeta function, then the Riemann hypothesis, as pointed out, as explained in the 1859 paper, is equivalent to the statement that this Laplace transform as a function of the complex variable w has all the zeros are pure on the pure imaginary axis. That's the critical line. It's been, by change of variables, it was transformed from the usual variables. But now Polya had the idea of doing this perturbation.
Please mean pure imaginary.
Oh, sorry. Excuse me. That's my abbreviation. Maybe I wrote that. Oh yeah. So sorry. I should have mentioned that. Thank you. Yeah. So when the zeros are all pure imaginary, I'll just for a short abbreviation, I'll say that the function has the pure imaginary zeros property, PIZ. Thank you. Right. So the Riemann hypothesis is equivalent to the statement that when the little lambda is 0, you have this pure imaginary zeros property, and that was already known by Riemann. Okay, and now Polya had the idea of putting in this perturbation, multiplying in the Laplace transform by the extra factor e to the lambda u squared, little lambda u squared. And he had the idea that maybe even with the perturbation, excuse me, the one you're really interested in is lambda equals 0, little lambda equals 0, but maybe even when you perturb it, you also have the pure imaginary zeros property, and that was his kind of idea of perhaps proving the Riemann hypothesis by proving something more general, even with this little lambda perturbation. But in the process of thinking about that, he proved some important features, which is that if you have the pure imaginary zeros property for some value of lambda, say lambda 1, then when you make little lambda bigger, that only helps. It doesn't hurt the pure imaginary zeros property. So increasing lambda sort of helps, decreasing could hurt. But he hoped that maybe even though it could hurt, maybe it didn't hurt. And even if you made lambda negative or even arbitrarily negative, maybe you still had the pure imaginary zeros property. If that were true, that would be, might be helpful in proving the Riemann hypothesis. You prove something stronger, and you get the Riemann hypothesis then as a corollary. He had a number of papers about that in the 1920s. The next major result that I want to mention is due to the Dutch mathematician DeBruijn in a 1950 paper. And he proved that the Riemann hypothesis has to do with the case little lambda equals 0. He proved that if you make lambda, if you help things, right, that help the PIZ property by making it at least the size 1/2, then you do have the pure imaginary zeros property. The 1/2 comes because it was using extending methods of Polya, that because you start out knowing that the zeros are in a critical strip, and the putting in the lambda with a positive lambda helps things. It actually squeezes things from the original strip, and if you squeeze it enough, it will push everything from the strip onto the center line of the strip, which is the critical line, which is here the imaginary axis. So, and he did a kind of quantitative version of that, and the result was that if you help things along by making lambda at least the size 1/2, even if the zeros weren't all on the imaginary axis, the critical line before, they will be when lambda is 1/2. So that was his result. Then I did a paper about 25 years later, which is now more than 40 years ago. I regard myself 40 years ago as almost a different person. So
then you can quote yourself.
Yeah, so I can say, well, what a clever paper this was. I'll explain a little bit later what motivated me. I wasn't motivated by analytic number theory or the Riemann hypothesis. I was motivated by some questions from statistical physics. To study questions about this kind of this Polya type question, but for different reasons. But a kind of an offshoot of that work, which was reported in this paper, was that if remember that from Polya that making lambda more negative can hurt things, and even though Polya hoped that maybe you would have the pure imaginary zeros property even if you tried to hurt things by making lambda negative, I proved that eventually you will hurt things. That is, eventually if you make lambda sufficiently negative, you find there's some value where you don't have all zeros pure imaginary. If you combine this kind of monotonicity result of Polya together with this result of mine, that eventually things are not all pure imaginary zeros, together with DeBruijn's, that if you help things that by an amount 1/2 they are, then you conclude that there's a dividing line, there's a dividing constant between when the zeros are pure imaginary and when they're not, which is here called capital lambda, so that you have the pure imaginary zeros property once you're equal to capital lambda or above, but not for lambda strictly less than that, and that capital lambda can't be any bigger than 1/2 by DeBruijn's result. It has to be strictly bigger than minus infinity by my result, and this thing is for some years now that constant has been called the DeBruijn-Newman constant. Except for people who mispronounce my name and call it the DeBruijn-Newman constant. Okay, now, so remember, the Riemann hypothesis itself, there was no little lambda. You were interested in the case little lambda equals 0. That's the same as saying that this capital lambda is either 0 or negative. That is, either maybe it's negative, meaning even if you hurt things a little bit, it still have only pure imaginary zeros. But if you don't do anything, then you certainly will have pure imaginary zeros, and that would be the Riemann hypothesis. If capital lambda was strictly positive, that would mean the Riemann hypothesis is false, and you have to help it before you get the zeros to be all pure imaginary. So the Riemann hypothesis is equivalent to the statement that this constant is less than or equal to 0. There's something sort of psychologically satisfying about, probably not mathematically significant, but psychologically satisfying about reducing the Riemann hypothesis to a statement about one number. Anyway.
So you said that you don't know that much about analytic number theory, but if lambda happens to be strictly negative, then the Riemann hypothesis is true, but does this bring more information?
The
original problem?
The short answer is yes. At least it gives you more information about the zeros, just than that they're. However, as we'll soon see when I continue the history, that question's not so relevant anymore. Right. Okay. But let me get there a little bit more slowly. So the Riemann hypothesis is equivalent to the statement that capital lambda is less than or equal to 0. Let me just kind of review what I just did. The first two lines are just reviewing things I already said. This constant, DeBruyn's result paper showed that the constant was less than or equal to 1/2, because that's all you need to, that's how much you need to help. That's enough of a help to get the zeros pure imaginary. And my result was basically that the constant is strictly bigger than minus infinity. So there is something in between minus infinity and 1/2. In that same paper, I made the conjecture that that this constant, if the Riemann hypothesis is capital lambda less than or equal to 0, I made the sort of complementary conjecture that it'd be greater than or equal to 0, which means that if you hurt it a little bit, it won't be true anymore. So if it's true, it's only barely so, in the sense that even a small perturbation of this kind will get some of the zeros off the imaginary axis. Yeah, so since I, as my younger self was not, young enough that not to worry about making extravagant conjectures. Okay. So here's some more history since that paper. So there were two bounds, right? There's DeBruyn's upper bound of less than or equal to 1/2, my lower bound strictly greater than minus infinity, and now here are improvements of those bounds over the years. So after about 10 years after that paper. There was a paper of Chordosh, Norfolk, and Varga giving a concrete bound. I didn't even try, didn't even occur to me that you could, should have, but it didn't, you could get something better than strictly bigger than minus infinity. Anyway, the people who are sort of interested in analytic number theory sort of realized that you could get bounds basically by looking at places where there are zeros of the usual zeta function on the critical line. Pairs of zeros close to each other give you, our way of studying those are a way of getting more concrete lower bounds. And there were a whole sequence of papers that got better and better. This was the first one, minus 50. Well, minus 50 is a lot better than minus infinity. But then I'm not writing down all of them. But they got progressively better, and here it's minus something times 10 to the minus 6, and then 8 years ago there was a paper that got it down to minus 10 to the minus 11th. So these were all inching their way towards this conjecture. The only improvement of the upper bound was a single paper about 10 years ago by Key, Kim, and Lee, which doesn't look like much, but it's better than it looks. It went from less than or equal to 1/2 from DeBruijn to strictly less than 1/2. But I'll mention something later which points out one of the other things in that paper which show that their results were, a lot better than just getting strictly less than instead of less than or equal. But that was the only improvement of the upper bound.
So the strategy to get this lambda to the 10 to the minus 1 was also always based on these points to be very close?
They were always based on close spacings of the zeros of the zeta function on the critical line. And we'll see, now I'm going to talk about the much more recent results about this conjecture, which does that kind of analysis in a more serious way. Okay, and that's right here. So that's about 1 year old. That's a paper of Brad Rogers and Terry Tao about a little over a year ago. And they actually, that series of improved lower bounds obviously were, evidence in favor of the conjecture, but, it wasn't at all clear that it was leading towards a conjecture. But in fact, it turned out, at least in the hands of Rogers and Tao, that some of those ideas could be used to lead to the conjecture, to proof. So they actually proved that conjecture. And what they did are sort of a couple of things. First of all, already in one of those papers, I think it was the second one I mentioned, Shorter, Smith, and Varga, they already began studying the idea that you can look at the zeros and watch how they move as a function of the parameter t. T is now replacing lambda. Think of it as a time. This function itself actually satisfies an inverse negative time heat equation. Heat equation moving in the wrong time direction. But then the zeros, assume the zeros on the critical line for a moment, then the motion of the zeros as a function of t is a system of ODEs, and once they get on the critical line, they sort of repel each other. You can see that from the formula, and because they repel each other, that tends to make the spacings equalize. They're all repelling each other. And so if the zeros are close together, that sort of means they haven't been repelling each other for very much time, if there's some zeros very close to each other, compared to typical spacings of the zeros. And Rogers and Tao made a serious study of that kind of phenomenon, and eventually used it to show that if the capital lambda were negative, then by the time you got to little lambda equals 0, this heat equation and motion of the zeros had enough times to kind of make the spacings move apart because of the repulsion, so that the distribution of the spacings would be sufficiently regular that it would contradict some known facts about the spacings of the zeros.
The spacings is supposed to be like the GUE.
Right. So I was just going to say that there are at least heuristic connections with spacings of zeros in random matrix ensembles, and of things like Dyson-Brownian motion and things of that sort. I don't think those things are actually used in the proof, but somehow the ideas from it are kind of relevant.
But if you look at the smallest spacings, very on the critical line, high up, they really do behave like the smallest spacings of the GUE. This has been tested by Paul Bourgade and myself, numerically. So they are, of course, up to 10 to the 30 zeros.
Right. Yeah.
And so, of course, they are very regular. The small spacings cannot be too small.
Right. So, yeah. So, part of the Rogers and Tao proof is that if the capital lambda were negative, then by the time the t has gone from that negative value to 0, the spacings have become regular enough that the sort of distribution of spacings compared to mean spacing over certain intervals would violate some results that were already known about the actual zeros of the zeta function. Okay, so that's the current status of the lower bound. The upper bound, there is also is some progress. So I mentioned this 10-year-old result of Key, Kim, and Lee. So here, down here is related to the comment I made before. Their result was more than just replacing less than or equal by less than. So, for example, one thing they show is that if for any positive lambda, even a small one, you may still have zeros off the real axis if you haven't proved the Riemann hypothesis, but only finitely many of them. So that sounds much more non-trivial than just changing the less than or equal to less than. And that thing is being used in a new project in the one of these polymath projects that Tao is also involved with, of trying to improve the upper bound. So, a result lambda less than 1/2 kind of begs for getting something better. If you can get less than 1/2, why can't you get 0.49? So so this project, which you can look at, it's still ongoing. It's a combination of some hard analysis together with serious numerical analysis, much of which can be made rigorous or eventually made rigorous. And the last, these slides were done a few months ago, but I just checked today, and the status is the same as a few months ago. So they seem to have gotten the upper bound, but using some serious numerical things combined with rigorous analysis, down to 0.22. This possibility of 0.11, I'm not sure how serious that is, but as far as I can tell, nobody seems to think that this, improving this will lead to the Riemann hypothesis. Okay, so now I want to spend some time. I said before that my own motivation came not so much from, for that old paper, came not so much from analytic number theory as from statistical physics. So I'd like to give a little bit of a hint of what that was, what that's about. It will be. Well, those who know a little bit about that will recognize it. Other people, I hope you get at least an idea. The interest in mathematical physics with this kind of question about the zeros originates in a 1952 paper about Ising models. Ising models are well, it was mentioned already in Gerard's talk. These are probabilistic models with variables taking values plus or minus 1 with certain kind of joint distribution, and they've been studied in the statistical physics literature since it was invented in the 1920s, the Ising model, and they've been studied ever since. There was a paper by the famous physicist P.D. Lee and C.N. Yang, actually a pair of papers in 1952, around the same time they did their work, which eventually won a Nobel Prize, but that was different work unrelated to this. And in the second of those two papers, they actually have a theorem, not just a conjecture or an actual theorem with a proof. Mark Kotz had some role in discussing with them how you write a proof. I mean, I think Young at least, I think, more or less knew how to do it. But in any case, I won't even state the theorem, but let me just say that kind of what it leads to. You can generate certain random variables and corresponding probability measures, distributions, which are called rho, from them, so that if you look at this Laplace transform for that rho, the rho would be some measure, actually be a sum of point masses on the real line, automatically an even measure like we said we want. And if you take lambda either to be 0 or non-negative, you'll have this pure imaginary zeros property. So that's a corollary of the theorem of Lee and Young. And it turns out that it would take a whole separate talk to try to explain why that's of interest in statistical physics, but it is. And because it was interested in statistical physics, it also was interested in a subject called Euclidean field theory or Euclidean quantum field theory, which is a kind of, you can think of it as something like an Ising model, except that the Ising model, the variables take values +1 or -1. So you're dealing with measures which are discrete measures, only have finally many values. In Euclidean field theory, you replace those plus or minus one valued things by measures which have densities that are continuous distributions, so they might have a density of the form e to minus some potential. And then this pure imaginary zeros property, if you have it, is very useful for all kinds of technical reasons. And so people who were studying Euclidean field theory in the 1970s were quite interested in questions like what sorts of functions v can you have here to create a function f so that you have that pure imaginary zeros property. And furthermore, because of the way things are set up in Euclidean field theory, it's natural to have this perturbation, this lambda, this e to the lambda x squared perturbation of the function f, because that corresponds to, in field theory language, to putting in a mass term in the Hamiltonian. And so it's particularly good for Euclidean field theory if you have an f where you would have the pure imaginary zeros property even when you do your best effort to make it worse by making lambda arbitrarily negative. So for the purposes of this talk, I'm calling such an f perfect. It's a very bad term, but and it doesn't appear, I think, in any of the actual papers. But so that's a nice property, and that was the property I was interested in.
Perfect means that the Newman constant is negative infinity.
Yes, for that right. The analog of the DeBruijn-Newman constant for that f would be negative infinity. Exactly. And there were some known examples. One of the things that was much studied in Euclidean field theory were the so-called phi to the fourth field theory models. And those correspond to a function v, which is a quartic polynomial, like constant u to the fourth plus or minus a constant u squared. And that was actually known to have this property of being perfect. In the statistical physics literature, that was proved in a paper by Simon and Griffiths in 1973. But actually, Polya already knew that, or most of that, back in the 1920s. I mean, the Simon-Griffiths result is somewhat more general than the Polya result, but stated this way, it was already known by Polya. Simon-Griffiths didn't know anything about Polya's work, and in any case, Polya's results wouldn't have been quite enough for the purposes of Euclidean field theory. But anyway, there's an example where because the B is arbitrary, positive or negative, you can put in this lambda is just changing the value of B, and you still have that property. So that was a very useful property of phi to the fourth field theories. And there were other field theories that one wondered whether they might have that property too. And the one that I was wondering about at the time was replacing the u to the fourth by hyperbolic cosine. That's a, well, it's a different even function of u. So I was interested whether that hyperbolic cosine, you might also have the perfect property. If you did, that would be very useful for constructing field theories of that sort. And I was disappointed when I was able to prove that you didn't have that property, basically by figuring out the entire class of all perfect Fs, which later on, if I don't run out of time, I'll more or less write down. And that classification showed that this e to the minus hyperbolic cosine was not perfect, so you don't have this property. That was a disappointment. On the other hand, it also showed that the capital phi of the Riemann hypothesis didn't have that property. So I decided to make the best of a failed result in field theory by writing a paper focused on the Riemann hypothesis. And the fact that you don't have that property for phi is another way of saying that this capital lambda is strictly bigger than minus infinity, and so that turned out to be a considerably more interest in number theory than in, it was a negative result in statistical physics, but in a sense was a kind of a positive result in number theory. Okay, so here's a so that well, except for the result of Rogers and Tau and this Polymath 15 project, most of those things are fairly old. So here's a more recent result that I did with Wei Wu. So it doesn't have anything to do with the Riemann hypothesis, but it's in the spirit of these kinds of questions. So if you replace the capital phi that's you're really interested in the Riemann hypothesis by a general little f or a measure rho, then you can ask the same sorts of questions. Mike and Gerard's question, for any f or rho, you can kind of define an analogous DeBruijn-Newman constant. And in this paper here, we actually kind of characterized a bunch of different possibilities of what the DeBruijn-Newman constant looks like, depending on tailed behavior of the f or the rho. And here's an example of one of the things that comes up there. And I'm going to mention this. So the part of the talk from now is more probabilistic than the previous part, so I apologize for non-probabilist. So here's an example of a theorem, and one reason I want to mention it is because the proof of it is kind of unexpected. So suppose you start with a measure rho. Let me write down an example. A measure rho where you where if you perturb with a positive lambda, you get something non-integrable. So the rho has a tailed behavior at plus or minus infinity, which is not as fast as any Gaussian. So it might be Cauchy distribution, constant over 1 plus x squared. It might be an two-sided exponential, e to the minus absolute x, or e to the minus absolute x to the 4/3. So in a case like that, then you satisfy this condition. If you try to perturb it with a positive lambda, you get something non-integrable, no matter how small. If you perturb with a negative lambda, of course, you get something that's nice and integrable, and it has this Laplace transform, but the theorem says any such lambda, you don't have the PIZ property. So that would mean that this analog of the DeBruijn-Newman constant for this rho is minus infinity. There's, you never have the pure imaginary zeros property. Okay, so that's well. There is some. Oh well, there's a comment. There's something called Gaussian multiplicative chaos, which this result can be applied to, which gives you a negative result about pure imaginary zeros property in that context, which is perhaps of some interest, but for the purposes of this talk, the main reason I'm mentioning it is because the proof is based on another theorem, which I call theorem B, which I'll show in a second, which even though we prove it and it's a result, well, it's reviewed in this paper, but we have another paper from a year or two ago where that result is stated and proved, which I still find somewhat surprising, and probabilists or analysts will sort of recognize why it's somewhat surprising looking. So here is, well, before I do the theorem, I have to give a definition. So again, since I said this was the more probabilistic part of the talk, so I'm going to use probabilistic language. Even though I write things in terms of random variables, it's really, all the statements are really, have to do with their probability measures or distributions on the real line. So I'm going to define a class of random variables, really a class of probability measures, which have two properties: evenness, so the measure under reflection of the variable u is unchanged. It's a measure which has at least Gaussian tailed behavior for some positive b. So you can multiply by e to the b little u squared, and you get something integral, at least of b if small. So not e to the minus absolute u or e to the minus absolute x doesn't qualify, or e to the minus absolute x to the 3/2 doesn't qualify. I don't know, 1 over 1 plus x squared e to the minus 1/4 x squared, that's fine. That's the second property. And you have this pure imaginary zeros property before you do any perturbation. So that's what this class Z is. Those are the random variables which you automatically come up from the theorem of Li and Yang in Ising models. So here is the theorem. Suppose you have a sequence of such distributions or random variables. Okay, the theorem, I'm going to skip the important thing in the parentheses here for a moment. The theorem says if you have a sequence of such random variables and they converge in distribution, that's the weakest kind of convergence you have in probability theory. It just means that it sort of integrate the measure against a continuous function of bounded support, and that will converge. Or if you prefer, look at the Fourier transform, and that converges pointwise on the real line. It's the weakest sort of convergence you could have. Then the limiting distribution or random variable is in the same class. Okay, that doesn't look too strange, but let me point out that this assumption assumes that each one of these has this Gaussian fall off of the tail, but there's absolutely no uniformity assumed in how fast the fall off is as a function of n. You could have a Gaussian fall off, but where a priori where it decreases, where the Gaussian fall off gets smaller and smaller as n gets large. Nevertheless, it says, even though besides that you're assuming this very weak convergence, the limiting variable is in the class and therefore has Gaussian fall off with some strictly positive b. That sounds like you're saying something that's impossible. It sounds like you're saying, I have a sequence of random variables with bounded second moments, but I don't care what the bounds are, and a convergent distribution, then the limiting random variable would have a finite second moment. That's simply not true. So it doesn't seem right. Of course, there's an extra assumption here, which is the pure imaginary zeros property. So it's not clear that it's false. And we claim that it's a true theorem, even though there's no uniformity. Somehow the nature of this pure imaginary zeros property forces there to be uniformity without assuming it. That's okay. So, and I remember first thinking about this result and not believing it, and eventually, once you prove it a few times, you start believing it. Okay, well, here, I think I'll skip this. This shows how you get that theorem A from this theorem B. Theorem A was, a certain kind of distributions like Cauchy or e to the minus absolute x, where when you perturb it in the wrong direction, you immediately get don't have pure imaginary zeros property, and it uses this theorem. So this theorem can be used to get kind of concrete results, but I'd rather skip this thing, even though it's rather simple. And I'd rather just say a little bit about sort of some of the ideas behind the proof of this theorem, and related to that is the original proof of that 1976 paper. And I think this is more or less the last transparency. So here's the key to that proof of this last theorem I wrote down, which I said is sort of surprising. You have to use this pure imaginary zeros property. The pure imaginary zeros property can be used. You have a function with a Gaussian fall off, so you know that this Laplace transform, which is the moment generating function, cannot grow in the complex plane faster than e to the a constant times absolute z squared. So it's entire of order 2 in finite type or something like that. And furthermore, by assumption, all the zeros are pure imaginary, so you can do a Hadamard factorization where you express this entire function in terms of a product over the zeros. The zeros are pure imaginary, but by the evenness of the distribution, they come in pairs, plus or minus I, y, k, where y, k is real. And so the Hadamard factorization, you get 1 minus z over I, y, k times 1 minus z over minus I, y, k. You multiply those two together, and you get this. And then nothing, again, by the evenness, the only other thing that you can have is an overall Gaussian-looking factor. So that's what you get for the Hadamard factorization of this Laplace transform or moment generating function. And furthermore, this is a moment generating function, which means that the second order Taylor coefficient at z equals 0 is the second moment up to a factor of a half. And if you write that down, that's here. The second moment is, there's a factor of a half, or 2. B plus the sum of 1 over y sub k squared. Okay, and the sum over 1 over y k squared has to be convergent because of the information you have about the order of this entire function. The point is that the point is something like the following sort. Well, there's sort of two parts. One is that you first show, so remember I compared this theorem to something which isn't true, where if you have a sequence of random variables which have, each has finite second moment, and they converge in distribution, and it doesn't have to be that the limiting variable has finite second moment. because of this representation, if you threw in an extra assumption, not just convergence distribution, but assume you have uniform bounded second moments for the sequence of random variables, add that, and then see how the second moments, which are given by this formula, kind of appear in this factorization. It's not too hard to believe that that extra assumption would be enough to give you kind of uniform bounds in this whole function in the complex plane, and then that should be useful in getting everything you want. So that's like half of the proof, that it's enough to add only one extra assumption, which is uniform bounds on second moments. The other half of the proof is to show that if you don't have uniform bounds on the second moments, then you can't even have convergence and distribution. That requires looking at not the moment generating function, but the Fourier transform, and showing that if the second moments aren't bounded, then those things cannot converge even pointwise. Anyway, that's the sketch of the proof. Then these factorizations are also relevant for the result that I did in 1976, that is completely classified these perfect functions f, and they look somewhat like this, but a little bit more complicated. You have an extra factor, and instead of having this assumption on the 1 over yk squared, you can have somewhat more divergent y sub k's, but somehow in some vague sense, the class of these perfect U's, one example we already said before was this thing that comes up in phi to the fourth field theories that's over here, and now you have something which is a kind of perturbation of them by a infinite product thing, but somehow it's a very restrictive class, and it's not hard to show, a little messy, but not hard to show that the capital phi of the Riemann hypothesis is not of this form by looking at tail behavior, and so that's how that characterization gets used in the proof that capital lambda is strictly greater than minus infinity. Okay, so you should be pleased to know that that's basically the end. Thank you.
red center again.